Okay. Okay, welcome back. Last lecture this week. Okay. Hopefully you haven't gotten tired of me already. But Josh will come back next week. Again. So today, this is kind of connected to the last two lectures, but slightly separated. Okay. So last lecture we talked about is this distribution, right, of your sample mean or your sample characteristic, and we talked about how we build these, how we use these parallel universes to build this distribution. So today we're going to talk about how do we actually build this parallel universe of samples. Okay. Some announcements. So project A2 is going to be due tomorrow, Friday. Please complete the mid-semester survey. You will get a password once you complete it, and then you'll need it for your project A2. Oh, okay, that's it. So let's talk about today's content. Okay. So as I said, right, last lecture we saw this example with the this warehouse with 32,000 pieces of paper. On each paper, we have the height of a Berkeley undergraduate student. Okay, and what did we do last time? Well, the whole idea is that we don't have access to this warehouse, right? We don't have access to the heights of all 32,000 Berkeley students. So we sampled 100 from here, right? And then we computed the mean, right, of our sample. So in random variable notation, right, we're sampling, right, we have 100 random variables, x1 through 100, and their ID, right, because we're drawing with replacement. And we computed the sample mean, say is 68.1 inches. Okay, and that's our guess, right, for the population mean, right, for the mean. So for the average, for the average height, right, for all 32,000 Berkeley undergrads. Okay, and last lecture we talked extensively about how to evaluate whether this is a good guess or not, right? Ran a little short at the end of the lecture, so I made a separate recording. Is kind of in the same place where the lecture recordings are. Okay, so make sure you take a look at that. But today we'll pick up from here. Okay, so again, right, we only get to draw 100 samples, right? We don't get to draw more, right, another 100. We only get to do this once. But you can imagine that in a parallel universe, right, someone else does this study and draws another 100 samples, and their sample mean might come out to be, say, 69.2 inches. Okay, and then you can imagine that among the multiverse, right, in all of the universes, you will exhaust, right, the number of possible samples. All of the possible combinations, right, of 100 Berkeley undergrad. So effectively, that's infinite, but there's a really large number, at least. Okay. But the problem is we only get to observe one of these, right? We only observe the 68.1 that's in our universe, or we don't observe the other ones. Okay. Yet, yesterday we relied on this tool heavily, right, where we have a distribution for the sample mean, right, by the central limit theorem. But if we only get to observe one of these sample means, where does that distribution come from? Right, there's no distribution; it's just a single number. Right? So where does that variability come from? Okay, so that's what we're going to talk about today. Methods that we can use to build this distribution. Okay, idea you have seen in data 8 is called bootstrapping. Okay, this is our main focus of the day. Okay, so one simple example of how bootstrapping works, right, is say I'm interested in saying something about the company that makes M&Ms. Okay, so I buy a bag of M&Ms. There's 18 M&Ms in it. And say I'm interested in the number or the proportion of M&Ms that are of primary colors. So red, green, and blue. Okay. So in this bag of 18 M&Ms, I see 9 M&Ms with a primary color here. Okay. Okay, so if I want to make a distribution, right, about the proportion of M&Ms that are primary colors, what I can do is I can take a bootstrap sample, right? That sample with replacement of the same size as your original sample, right? So there are 18 M&Ms here, so I'm gonna sample with replacement 18 times at random, okay? So say this is my first bootstrap sample, right? Of course, this is synthetic, right? This is not our original sample that, we draw from that all the M&Ms from the factory, right? This is only a resample of our original sample, right? So we call it a bootstrap sample or a synthetic sample, right? So say in this sample, we have 7 M&Ms with primary colors. Because we're drawing with replacement, you're allowed repeats, right? You could draw the same M&M many times, okay? Say for another sample, right? There are 11 out of 18 primary colored M&Ms. And you can keep going, right? Say we draw 10,000 samples. So then, right, what do we have? Outside of that 9 out of 18, right, proportion of primary color M&Ms from our original sample, we also have, right, 10,000 other proportions, right? Those are from the bootstrap sample. And that itself can build a distribution. Right? So this is how we create parallel universes, right? We don't get to observe, right, if you just keep sampling 18 M&Ms from the factory, but we can keep sampling from our bag of 18. Okay, so why does this work? That's what we have to think about, right? Why does the bootstrap work? Again, this is kind of a review from data 8, but it might be a while. So the whole idea, right, is, now we're going back to the highest example, right? The whole idea is I don't have access to my entire population, right? I don't know the heights of all 32,000 Berkeley undergrads. So I take a sample of size 100, and it's a random sample. So from the sampling lecture, right, you know that if we want a random sample, our goal is to make the sample resemble the original population as much as possible, right? The structure, right, of like the distribution of heights in the original population, should be captured by our random sample, right? So if we have, say, a higher proportion of people that are, 70 inches tall, you should also have more 70 inches people in your sample as well, right? So it'll be representative of the population. So then, if your sample is good, right, your sample is representative of the population, what we can do is to regard the sample as our population, right? It is kind of a downsized version of the population. So whatever the population has, right, the sample should also have. Okay, then, right, if we regard the sample as a population, now our bootstrap sample is simply just, we're sampling, say, 10,000 times, right, from the population. Right? Although we're sampling, right, we're sampling from this original sample, but you can regard it as 10,000 samples from the population, because your original sample in blue, right, is really representative of your population. So that's why the bootstrap works, right? The bootstrap is just basically first creating kind of a downsized version of your population and then keep sampling. Okay. And again, right, all of these are done with replacement. So you're allowed duplicates, right? You're allowed the same sample to be, the same observation to be included in a sample many times. Okay. So let's look at an example. So here, let's go to the demo. Okay, hopefully this is big enough, but not too big that everything should show. Okay. Let's start here. Oh, no, don't start here. Let's read in. So here I just kind of made up 10 numbers, right? These are, suppose, right, instead of 100 sample of size 100, we just sample 10 students out of all Berkeley undergrad students, okay? And the mean of our sample is 67.6. Okay. And now, right, to do the bootstrap, we're going to regard this as our population. Right? Of course, Berkeley has more than 10 students, but we're hoping that these 10 numbers would represent well the whole population, which we'll talk about how to kind of make sure your sample is good enough, okay, in a bit. Anyways, now down here, what I'm gonna do is I will draw a bootstrap sample, right? So this np.random.choice is gonna sample from this heights list, right, of 10 heights, and I'm gonna sample 10 times, right? So how many ever long this heights list is with replacement. And then I'll compute the mean of this bootstrap sample. Okay. So here, we see this is the data for my original sample of 10, right? So the average height is 67.6 for that sample. And now, right, I'm making one bootstrap sample, right? This synthetic 10 numbers. And you see that because in the original sample, you have so many 66, you also have more 66, right, in your bootstrap sample. And then here, the average for this sample is 67. Okay. And now we're gonna do is we're gonna stuck that code snippet into a for loop, and then we'll do it 10,000 times. So we're drawing 10,000 bootstrap samples. All right. We'll do 10,000, and then for each bootstrap sample, we're gonna compute the sample mean, right? So we will have 10,000 sample mean. And then these are the first 5. Okay, and then just to visualize it, let's put it in a histogram. So this is a histogram of heights, of sample mean, right, of the heights from the 10,000 bootstrap samples. Okay, so there's 10,000 values in this, and each is computed on a bootstrap sample from the original sample. Okay, so where does our original value lie? What is the original value again? 67.6. So somewhere in the middle, right, in the bulk of it. All right. So what can we do now, right? When we have this histogram, right? When we have this 10,000 sample means, we're able to build this bootstrap distribution. Right? And with a distribution, there's many things we can do, right? You've seen this in data 8. One thing you can do, right, is to create a confidence interval, right, of the true population mean, right, the true average height of all 32,000 Berkeley undergrads. Right? So here it is, right? Basically, what you do is you take say I want a 95% confidence interval. I just take the middle 95%. Right? You use that percentile. Where to go? Yeah, use a percentile function. Okay. So here, right, this is my confidence interval. So the lower bound is 65.6 and the upper bound is 69.4. Okay. So hopefully you should start kind of remembering these from data 8. Right? We use the bootstrap a lot in data 8. Very powerful, very versatile. And another thing you can do, right, now that you have a distribution, is hypothesis testing. Right? So perhaps, right, we can say for our null hypothesis, the true population average, right, the true average of all 32,000, true average height of all 32,000 Berkeley undergrads is 68 inches. Okay, we want to run a hypothesis testing on that, the hypothesis test on that. And where is 68? Well, 68 is kind of in the bulk of my distribution, kind of in the peak. Not exactly at a peak, but quite close, right? So what that means is that, yes, it is likely, right, that I draw a sample of 10 and my sample mean end up being 68, right? So sorry. Yeah, it is possible, right, to end up with a bootstrap distribution like this if your true population average is 68. I think that's more precise. Okay, so in hypothesis testing terms, means we cannot reject the null. Remember, you cannot prove the null, you can only fail to reject it. Anyways, that's the kind of the idea. Okay. Any questions so far before we talk more about this distribution and these estimates? Okay. So from last lecture, we saw these couple quantities of an estimator, right? So here, right, we're using the sample mean to estimate the population mean. So right here, right, this theta hat, the estimator is x bar, right, the sample means, and theta is mu, right, is a true population average. And we said, right, we cannot compute, right, numbers for these quantities because we don't know the underlying data generating process, right? We don't know what theta is, right, or what mu is, right? So how can we compute these, right? We don't know the distribution, right, that's used to generate our data. So how can we compute, say, the expectation, right, of our estimator or the variance of our estimator? But now, with our bootstrap distribution, we can use this to estimate, right, the expectation and the variance of our estimator, right, of x bar, because this itself, right, is a distribution of x bars, right? The x bars I computed from my bootstrap samples, right? So it is a distribution of the x bars. So what are we gonna do? Let's start with expectation. So I want expectation of x bar, right? Here is theta hat, right? But x bar is really in our concept. So what is the expectation? It's an average, right? Weighted average, but it's the average, right? So how we can estimate an expectation is using the average of the x bars. So I have 10,000 x bars, right, from my bootstrap sample. I just average them, and I can use that to approximate my expectation of the estimate. Variance is the same thing. I just compute the variance of my x bars, right, to get the an estimate for the variance of my estimator. Too many words. Estimate, estimator. So let's just see this in action, right? So the synth estimates contains those 10,000 x bars. Okay, so right, to estimate the expectation, I can take the mean of it, right? And to estimate the variance, right, I can plug it into the variance formula, right? That is simply the values, right, in this synth estimates, and then you subtract the mean from it, square it, take the average of that, right? So take elements in this, take these 10,000 x bars, subtract by the mean of them, right? And then square it and average it. So that is the estimated variance, okay, of our estimator, our x bar. 0.92. And if you don't want to plug it into this formula all the time, or if you forget what the formula is, NumPy has this variance function that you can just use. So you're really just computing, right, the variance of x bars from the bootstrap sample. Okay. So you get the same answer. So this is the text set down below. This is kind of the main takeaway, right? Is we cannot compute the expectation of variance of our estimator without having full information about the population or the data generating process, right? You need the distribution of from your data generating process, or you need your entire population to compute the expectation of variance. But since we have our bootstrap samples, right, we can use that to estimate, right, these quantities that we can only compute with the knowledge of the population. Okay, right? Because your bootstrap acts like 10,000 samples from the population, which is quite nice. Okay, any questions on this? All right. So let's discuss. Bootstrap is really powerful, right? Really versatile. Like it works pretty much for most cases, right? Whenever you don't want to do the analytical solution of some analysis, chances are you can just use a bootstrap. Okay. So here's a question. Right? When is the bootstrap not good? Okay. When what scenarios might the bootstrap do a bad job of simulating the uncertainty around our best guess, around our estimator? When is a bootstrap not good? Or in other words, right? When will you have these? When would you have your bootstrap samples not being representative of your population? Right? What do we think? No right or wrong answers again, right? So just talk to your neighbors, take a minute or two, and then we'll discuss this. Let's wrap up our answers. Okay, so let's see what people think. Okay, small sample size, skewed, unrepresentative samples. Okay, the order matters. Okay, there's a, what is that emoji? Is that a stock market? Okay, I'll try my best to interpret what that means. Okay, and maybe some of you have peeked at the answer in the next slide, so don't do that. Don't spoil the answers. Okay. There are a couple of things that could happen. So think about again, why does the bootstrap work? The bootstrap works because our original sample, right, that one sample that we draw from the actual population, that sample is good. That's why your bootstrap works, right? If that sample itself is bad, then your bootstrap is not going to work, right? So here are a couple ways, right, that the original sample could be bad, okay? One, this is about sample size, right? So your original sample should be relatively large, right? That 10, right? Sample of 10 heights from 32,000 Berkeley undergrad. That's probably too small, right? Right? Because the larger sample is more likely to capture the structure of the population, right? There's not kind of a rule of thumb on how big to use. So as big as your budget and your constraints allow, I would say. Okay. Another thing, right? If your population itself is very skewed, there are some outliers in your population, there are some extreme values in your population, then your original sample is unlikely to capture that, right? Because there's so few of those individuals. So whenever it's outliers, always think about Bill Gates. Somehow that also works with me, like most of the time. Whenever there's an outlier situation, think Bill Gates. Okay, so imagine if Bill Gates lives in Berkeley and we're doing a survey about salaries or income, okay, or wealth, okay. So we're trying to estimate, say, the average income of everyone in Berkeley, and we draw a sample of, say, like 100 or 1,000, you know, 1,000 residents of Berkeley. Then Bill Gates himself is going to single-handedly pull the average income up, right, for Berkeley. But your sample is very unlikely to pick Bill Gates, right? Because out of, you know, the tens or hundreds of thousands of residents of Berkeley, there's only one person, right? The chance of picking Bill Gates is quite low, right? So as long as your sample does not pick Bill Gates, you're not gonna have that in your bootstrap at all either, right? So your bootstrap is gonna do a pretty bad job if your quantity of interest is the average income. Okay. In this case, right, maybe studying the median is better if you know there are a few very rich people in your city. Right? Another thing that where your bootstrap can fail. This is less about the sample, but more about the quantity of interest, right? So before we're always interested in, say, the average, right, of the heights or the median, right? These are kind of rather values in the middle of your distribution, right? But if you have something that's extreme, say, I want to estimate the best, the height for the tallest person at Berkeley, right? Then what you're gonna do is you're gonna take your original sample and then you're gonna bootstrap it and you're gonna take the max, right, of each bootstrap sample. Well, you know, one thing is that max is always going to underestimate the true max of your population, right? There's not going to be a scenario where there's one person in your that magically appears, right, in your bootstrap sample that's even taller than the tallest person in your population, right? That's not possible, right? If you're the tallest person in your city in Berkeley is, say, I don't know, like, you know, let's say 7 feet tall, right? There's no way that your bootstrap sample has someone that's 7'2", right? That's just impossible. So whatever your max of each bootstrap sample is going to be less than or equal to the max of your population. So you know you're underestimating, right? Same for the mean, right? You'll always be overestimating in that case. All right. Okay. Questions. Put it on. Do not disturb. Okay. Questions. All right. So just be careful, right? When you're using the bootstrap, these are kind of the things to look at. All right. So far, this is kind of a summary of what we have done. So far, we have been focusing on prediction tasks, right? Even these estimation tasks, right? They're prediction. So our goal, right, in prediction tasks are always, okay, I have, right, some response Y or a bunch of them, right? Y1, Y2, a bunch of them. And our goal, right, is to construct these Y hats that that try to get as close as possible to the Ys, right? We're trying to predict what a Ys can be to the best of our abilities. Okay. But we haven't spent a lot of time on kind of the mechanics behind the model or the interpretation, I guess, of the model, right? We're using X to predict Y, right? But how does X really relate to Y, right? Why does the higher X values contribute to higher Y values or vice versa? Or what is, right, the relationship between these? Okay. What are the features that we include in our model, but why, right? So why do we include these features? Okay. So these interpretation or kind of reasoning problems on a model are called inference problems. Okay, so that's a kind of a distinct or a separate problem from prediction. Okay, so just to compare, right? For prediction problems, which we have been doing in Data 100, the goal is always just to try to get your prediction, your Y hats, as close as to the response Ys as possible, right? So questions like, right, how much will the stock market go up tomorrow, right? You're predicting the price of stocks, right? Is this credit card charge fraudulent, right? The answer is yes or no, right? And you're trying to have the correct guess, right? Can my phone accurately detect my face, right? Your face ID. Josh put his face into one of the kind of those websites where it searches your face on the internet and it thinks he's this guy on Instagram. This is not him, by the way. But anyways, right? This is a bad prediction outcome, but still, right? The goal is to predict, right? Predict who this face is, right? So that's prediction. And what about inference? Okay, so inference really asks the question, right? In our model, how does or why does a certain feature relate to our response? Okay, so the question will be like, what is the effect of getting a college degree on life outcomes, right? What is the effect of a drug? How does raising the minimum wage affect the unemployment rate? Okay, effect, right, are the keywords here, right? We're trying to assess how does one variable influence the other, right? We're not trying to predict on people's life outcomes, right? We're trying to assess what factors, right, influence life outcomes, right? Okay, so then we'll talk about inference for a little bit. But you should also know that although we kind of discussed these two, prediction and inference, as separate categories, there is not kind of a clear-cut boundary between them, okay? Sometimes things are mixed up. One of the examples will be your credit score, right? So these credit card companies would build models to accurately, as much as possible, predict your credit score. But in doing so, it also wants to offer you some explanation on, say, why is your credit score lower than expected, right? So, right, the predicting credit score part, right, is prediction, but explaining why your credit score might be lower than expected, that's inference, right? So sometimes you need both, okay? And the inference part is often kind of more what people care about in certain scenarios, right? Like credit score. And now with the technology of AI and large language models, right? We kind of want to understand how these things behave. So that is the question to you. In identifying the most likely next word in the sequence. So that's pretty much how most large language models do, right? That's how most large language models communicate to you, right? It starts with a word and then it predicts, right? What is the most likely next word that follows the previous one? Okay, so in that identifying the most likely next word in the sequence, is this primarily a prediction problem or an inference problem? Right? So are ChatGPT is doing predictions or are they doing inference? Talk to your neighbors. And I don't think there's a right or a wrong answer in these. Yeah. All right. Well, with that lovely music, let's look at people's answers. Okay. So I think most people agree that it's a mix of both, right? But which one is the main focus here, right? That's the question, right? Well, so I will preface this by saying there has been a lot of research on explaining the behavior of large language models. Why does it choose a word over another? Right? A lot of studies. However, right, in building an LLM, the primary function of it is so that it can converse with you, right? Is that when it says, right, or not says, right, kind of when it types out a sentence, it reads like a sentence that a person would say or would write, right? So in doing so, right, what you're trying to do is you're trying to predict the next word that's that satisfy you as much as it can, right? By satisfy, I mean there are certain criteria, right, on these next words that you can evaluate it on. This is way beyond the scope of this class. But understanding why that word is selected, that's more of a secondary concern, right? You have to have it kind of read like a person first before you get to explain, right? Before you explain your word choice. But of course, right, in making this prediction, you're also doing kind of these, you're factoring a lot of features, right? You're considering the context, you are, considering your tone and things like that. Those can be also viewed as inference, but it's still at its core prediction. We're trying to predict the mood, right? Predict the context based on the prompt, okay? But again, right, it's basically there's no right or wrong answers in kind of these categories, especially when it comes to LLMs. It's really mix of prediction and inference, right? Where inference excels, however, is when you have a large language model trying to improve it, right? The understanding its behavior will be really helpful in improving the model, right? There's still ongoing research. We still quite don't understand how it makes certain decisions over others. Okay, so if you're interested, you should look into it. This is going to be a very big discovery if you can kind of fully explain the behaviors. Okay. All right. So we're gonna focus on inference for now, right? Predictions we have done for the past couple of weeks. So let's talk about inference. So even inside inference, there are a couple categories. Okay. So there's something that's called the correlational inference, right? So this is the inference that studies kind of the association of two factors. Things like, are homes with granite countertops worth more money? Do people with college degrees have higher life earning? And are people who smoke more likely to get cancer? Okay, so you see that in these tasks, these problems, we're only studying kind of the coexistence of these two factors. Granite countertops, higher value, right? Do they come hand in hand with each other, right? Do they often occur together, right? College degrees, higher earnings, right? Do they come with each other, right? We're not establishing causation, which is a harder task, right? So if you want to study the causation, right, under these contexts, here's how you would potentially frame them, right? How much do granite countertops raise the value of a house? Okay. Does getting a college degree increase lifetime earnings? The smoking cause cancer. Okay. So you see that the kind of the verb, right? The action verb is from one feature to the other. Right? So these are examples of what's called the causal inference problems. Okay? Also very, very popular area of research. Okay? But these, right, don't just study the coexistence of factors, right? They study the causal effects of factors. So, for example, let's look at this example. We're gonna use this a lot for the rest of the lecture. So correlation study, right, on college degrees and life earnings, right? The question you can pose is, do people with college degrees have higher lifetime earnings? And kind of the causal inference counterpart to this will be, does receiving a college degree increase lifetime earnings? So here's why, in many cases, causal inference is a lot more difficult than correlation inference. Okay? So this is from data 8, right? You also got introduced to the famous saying, right? Correlation does not imply causation. And what implies causation? How can you establish causation or causality? Is randomized experiments, right? You have to have randomized trials where you put people to control and treatment, right? In order to establish causality. Okay? So if you want to carry out, right, this causal inference problem, right, then you randomly assign each participant, for example, the avatar of Josh on Instagram, to one of the two groups, right? Whether, right, you have to assign them to get a degree or not a degree. And then you have to keep track of their lifetime earnings, right? Either way. And you do this for many participants. That's how you establish causality. Do we see a problem with this? Can we just randomly subject someone to getting a college degree or not getting a college degree? It's really unethical to do so, right? So also almost impossible, right, to control for this. Also, very difficult to keep track of someone's lifetime earnings, right? So most of the time we cannot conduct these randomized experiments, right? That's why we're confined to only studying the correlation between these two, because that you can study from just observing their degree status and their lifetime outcomes, okay? Another more extreme example is the smoking cause cancer. You cannot subject someone to smoking, right? But on the other hand, probably everyone knows, right? The kind of the established argument nowadays, right? Smoking does cause cancer. So how do people come up with that conclusion, right? How do they arrive at that causality, right? This is beyond the scope of this class. We have a class called Stat 156 that's entirely on causal inference. So in that class, you will learn about methods that can establish causality or kind of slightly weaker versions of causality without doing randomized experiments. Okay, so they're quite cool. It will also win you a Nobel Prize if you make big advances in this area. Okay. So today we're just going to talk about correlational studies within the inference realm. Okay. And the example we're going to use is the lifetime earning versus college degree study. Okay. So one way to study this relationship, this correlational relationship, is via a regression problem. Okay. You can frame this as if I want to predict someone's lifetime earnings, okay, with college degree status as a feature. So you can set up a simple linear regression model. And why does this work? Well, to think about the interpretations of theta zero hat, right? That's your intercept, and theta 1 hat, which is your slope. Okay, so what does your theta 0 hat do? Well, if this person has no college degree, right, the predicted lifetime earning will just be theta naught hat, right? So theta naught hat is the predicted lifetime earning for someone without a college degree, right? Because if they don't have a college degree, this term will just be 0, right? This is a 1 and 0 feature, right? They have a college degree is a 1. If they don't, it's a 0, right? So if they don't have a college degree, then we're just left with theta naught hat as a prediction. Okay. What about theta 1 hat then? Well, you can imagine, right? One person has no college degree, the other person has a college degree, right? The prediction for the person without college degree will just be theta naught hat, and the prediction for the person with a college degree would be theta naught hat plus theta 1 hat, right? So you have this extra theta 1 hat term for people that have college degrees, right? So one way to interpret the theta 1 hat is how much higher are the predicted earnings for someone with a degree compared to someone without. Okay, and again, right, the reason that this works, I'm just gonna try to write it out, is someone that has a college degree, right? Their prediction will be theta naught hat plus theta 1 hat. And for a person without, it is theta naught hat, right? So the difference is theta 1 hat. All right. So let's kind of follow this idea, right? We fit this simple linear regression model, and it turns out, right, that theta 1 hat is, so you see the 2 greater than sign, that just means it's much larger. Okay, so theta 1 hat, right, the parameter for the college degree feature is much larger than 0. Okay, is this strong evidence that getting a college degree increases lifetime earnings? Okay, yes or no? Take like a minute. This is a yes or no answer, so just pick one. Talk to your neighbors if you want to. let's finalize our answers. Okay. Let's see what people think. Wow. 50-50. That's like toss of a coin. So think about the wording of this. Okay. Don't change your answer. Think about the wording of this, right? Getting a college degree increases lifetime earnings. Is that a statement about correlation or causation? Causation, right? This increases, right, is implying that, right, having a college degree has a effect, right, has a positive, it causes, right, more lifetime earnings. Right? And why, right? But now we can think about why this is the case, right? Why can we not establish causation in our study, right? Simply speaking, right? Our study is not a randomized experiment, right? Because we have a data set that's with degree and non-degree holders, degree holders and people without a college degree, right? And we randomly sample from that data set, okay? That is not a randomized randomly, right? But here's the question. Why can we only establish causality with a randomized experiment? Right? Was that muted the whole time on Zoom? I don't think so. Okay, good. That would be really scary. Okay. Right. Then you'll be stuck with Josh's recording from last semester. Might be a better thing. I don't know. But anyways, so this is our desire study, right? We want to study, right, whether having a college degree would cause higher life earnings, but someone with a college degree might have some other traits, things like family wealth, right? Especially for people in private schools, right? It might be the case, right, that people having a college degree is associated more with a larger amount of family wealth, right? And perhaps, right, family wealth is the contributor to a higher lifetime earnings. Right, so here we do not know, right, which one of these two, having a college degree and family wealth, right, directly or contributes more, right, to higher lifetime earnings. Okay, so family wealth, this is called a confounding variable, right, or a confounder, right? This is a variable that also leads to your effect, right? But is not the factor of interest here. Right? Okay, so let's take a quick break. And then when we come back, we'll keep discussing what does a confounder do and how can we address and account for confounder. Okay, let's continue. All right, so confounders. What do we do with confounders? Well, one thing we can do, right, when we have these confounding variables, is just to account for them by adding them to our regression model. Okay, so now, right, on top of that college degree feature, right, which is the one I'm interested in, I just add, right, another feature that's family wealth in dollars. Okay, so family wealth amount. Okay, I might have to write here. Oh, I don't have to. Okay. So now let's interpret theta naught, theta 1, and theta 2 hats. Okay, so theta naught hat. Right? Well, you get predicted theta naught hat with nothing else if you have no college degree and your family has $0 in wealth. Right? So that's the interpretation for theta naught hat. What about for theta 1 hat? Well, for theta 1 hat, you will have to hold, so you can imagine that there are two people that have the same amount of family wealth. One has a college degree, one has not, right? So the prediction for the one that has a college degree will have the actual theta 1 hat term, right? So holding family wealth constant, how much higher is predicted earnings for someone with a degree compared to someone without? What about theta 2 hat? Okay. That's not the actual answer. It's telling me that I should go to the slide. How do you interpret theta 2 hat in this model? Okay. You should see the answer choices on your end. It's not displayed here. So take a minute or two, talk to your neighbors, see what you think. Okay, seems like number has stabilized. What do you think? Okay, majority selected the correct answer. Okay, so let me explain the answer, right? So we're gonna do some calculations. I'm gonna sit down so I can use my iPad to write. So we're gonna do some calculations here. Right, so we're gonna calculate the earning of 4 people. Okay, so the first one we're gonna calculate is the earning of someone that has a college degree and they have $1,000 in family wealth. Okay, so what is the prediction here? Is theta naught hat? They have a college degree, right? So they have a theta 1 hat plus what? 1,000 times theta 2 hat. Right, so that will be the prediction for the earnings for the person with $1,000 in family wealth. What about if the person has $1,001 and also has a degree? Right, same two terms, but here, right, this is 1,001. So the difference between these two predictions, right, where right, the only thing that's different for these two people is this $1 in family wealth. The difference is just a single theta 2 hat. Okay. What about for people with no degrees? They have $1,000 in family wealth, right? That's theta naught hat plus 1,000 times theta 2 hat, right? There's no theta 1 hat because they don't have a college degree, right? And then for this person with $1,001, right? So the difference here, right, is again theta 2 hat. Huh? So that's how we interpret theta 2 hat, right? It's holding the same, right, degree status, right, for a person that makes that has one more dollar in family wealth. How much higher is the predicted lifetime earning? Right? So you're holding the degree constant, the degree status constant. And this, right, effectively helps us control the effect of family wealth, right? Now we can separate, right? How does the college degree impact earnings, and how does the family wealth impact earnings? Okay. Now that we have this better model, right, that accounts for family wealth, do we have if, right, the fitted, again, theta 1 hat is much larger than 0, now do we have strong evidence that getting a college degree increases lifetime earnings? What do we think? Again, a yes or no question. So I'll give you like 30 seconds-ish to think about it. Wrap up our answers. Okay, so let's see what people think. Relatively 50-50 again. Okay. So this is the same argument, right? Okay, now that we have accounted for family wealth, there could be something else, right? There could be other confounders that contribute to increased lifetime earnings, right? That's associated with having a college degree, right? So there are other confounders that are observable, things like health, right? Demographics, geography, right? That would contribute to higher or lower lifetime earnings. But there are also confounders that are not even observable, right? Things like intrinsic motivation or value, right? How much do you value making money, right? Things like that, right? Those are not even observable, and they still act as confounders, okay? So in this kind of line of inference, a very again, right? We just cannot assume that we have accounted for everything. However, a big assumption that we make in these studies is we are able to observe all of the confounders, and we have accounted for all of the confounders. Okay, this is an assumption, a big assumption, but it's an assumption you make about your study, right? Because usually when you see a correlation or a causal study like this, you will see that they have a bunch of features that they collect on these people, right? So the assumption is that you have assumed, you have observed and collected all of these confounders. Okay, it's also called ignorability. So you can imagine there are issues with this, right? One, this is not really a verifiable assumption, right? You can't really prove that you have accounted for everything. right? But if you somehow manage to verify, right, verify your assumption, then it does imply a causal relationship. Right? So if you have accounted for all of the confounders, then you could establish causality potentially. This is why to be important to be open and documenting everything you do with your models. Okay. So the interpretation is clear. All right. Questions? Okay, so let's go back to our original model. Let's say we just want to run a correlational study with this. Okay, and then here's on the right where we show our data, right? Our X is just a single feature, and it's 0, 1, right? Whether a person has or has not college degree. And on the y-axis, right, you have the earnings of these people. And if you fit a simple linear regression over this, right, you get a line like that, but really you're only plugging in a 0 or a 1, right, to that model. Okay. So without accounting for confounders, right, your theta 1 hat is your estimated effect, right? Your estimated association between having a college degree and lifetime earning, right? So the theta 1 hat is a good number, a good quantity to study. Okay. So again, this theta 1 hat will depend on your sample, right? So if you draw another sample of, say, I don't know how big this is, like 50 people. So you draw another sample of 50 people, right? Your theta 1 hat will be different, right? So this goes back to our parallel universe sampling kind of problem. Is how do we assess, right, the uncertainty of theta 1 hats? The answer is bootstrap again. Okay, I'm gonna wait for this GIF to reset so I can show you. Yes, okay, here we go. So this is our original data. What we're gonna do is we're gonna take a bootstrap sample, okay, and then we're gonna fit a simple linear regression over it. I will take another bootstrap sample. We fit another regression model over that bootstrap sample. Right, and you do this over and over again. For each bootstrap sample you draw, you can estimate a theta 1 hat. Then say you do this 10,000 times, then you have 10,000 theta 1 hat, just like the X bars we talked about before, right? Then with the 10,000 theta 1 hats, you can do the usual confidence interval, hypothesis testing, estimating bias variance, all of that. Okay, so bootstrap. There is a demo for it. I don't think I have time to run through it. But just like the note says, everything we do today is probably more understandable if you do the demo yourself, right? It's easier to understand if you do the demo yourself. So play with the demo. There's a lot of writing in there too, so you can kind of get a sense of these ideas of bootstrapping. Okay. Last topic of the day, or the week, actually. So again, we're gonna stay with the lifetime earning college degree example. So we have, right, so in our regression model, we have, right, 0, 1 having a college degree. And let's say we put in that the feature for family wealth. And let's say we put in another feature, okay? Because why not? Right? So another feature we put in is whether this person has lived in a college town. Okay, so that's another feature that we put in. There's a problem with this, right? Adding this new feature is going to kind of hinder our inference about theta 1 hat, right? This effect of college degree on lifetime earnings. How is it going to hinder it? Let's think about it. Okay, so this is called something called multi-collinearity. I'll explain what it means in a second. Okay. So first, let's talk about the family wealth feature. Why is that a good feature to include? Well, remember when we were doing comparisons before, right? We're going to hold family wealth constant. So let's assume, right, that we have held family wealth to this high wealth category, right? Then, right, your theta 1 hat can be is a comparison between having a degree and not a degree, not having a degree, right? Holding family wealth constant. In this case, you're probably going to have a good amount of people, right, that have a degree and have high family wealth, and having no degree and high family wealth, right? You have a good amount of individuals to compare here. Same for the low family wealth population samples. So you can run a fair comparison. But think about how having a college degree relate to having lived in a college town, right? So most people probably will fall into these two categories, right? If you have a college degree, chances are you most likely have lived in a college town, right? College town meaning a town with a college in it, right? So very unlikely that you have a college degree and you haven't lived in a college town, right? Most likely you did like online college or something, right? Or if you have no college degree, chances are you have not lived in a college town. You could have just grown up in Berkeley, right? But that's a very small part of the population, okay? So now when you run comparisons, right? Say I want to hold college town constant, right? Because I want the effect of degrees on earnings. There's not a lot, right, in this category here to compare to, right? This is going to be really, really sensitive to the data that you collect, right? The value of earning is going to have a large variance, right? In these smaller categories. Okay. So this phenomenon is called multicollinearity, okay? Or just collinearity. This is when you input very highly correlated features into your model, okay? So here, right, the values for having a college degree and having lived in a college town are probably going to look very similar, right? If you have a 1 in a college degree column, you're probably going to have a 1 in the college town column, right? And vice versa. You have a 0 in the college degree column, you should probably have a 0 in the family wealth. Right? So why does that cause a problem? Right? Well, your model doesn't know which one is which, right? It just knows that these are two features that you put into the model. Right? So think about what happens. Fitting a regression model, your goal, right, is to minimize the mean square error or the root mean squared error. Okay? So think about the effect of, say, if I raise theta 1 hat a little bit, it's going to have the same effect on the RMSE as if I raise theta 3 a little bit, right? Same thing, if I decrease theta 1 a little bit, it's going to have the same effect of decreasing theta 3 a little bit because those two features are nearly identical, right? Following this logic, if I increase theta 1 a little bit and decrease theta 3 a little bit, it's not going to change the error that much, right? Because they kind of cancel each other out, right? So I could even raise theta 1 by a lot and decrease theta 3 by a lot, and it's still not going to change my RMSE. So it's still going to be as good of a model, right? In the error sense. Okay? So the values of theta 1 and theta 3 hats are going to be very sensitive to the data that you feed the model. Okay? And why is that a bad thing? Right? Then right? Then you can kind of freely change theta 1, theta 3 without changing the performance of your model. And that's going to undermine the validity of the interpretation of theta 1 and theta 3. Okay? So how do we deal with the multicollinearity? Well, drop one of the columns. That's it. Right? If you can imagine, you have a column that's height in feet and a column is height in centimeters, you drop one of them. right? So then you can solve this problem. Okay, so do care about correlated features is going to hurt your model more than you think, right? It's really, and then the word by multi-collinearity comes from this idea that your columns in your design matrix are linearly dependent on each other. Okay? That's where that word comes from. But yeah, so that's all I want to talk about today. And we are 1 minute early. That's really good. Okay, I will see you next week.